Hello everyone, welcome to my channel. Today we're going to solve some typical common exam style questions on topic chemical energetics for mostly AS level examinations. This also fits with IB curricula, AP levels, and also to NAS program. Alright, so let's begin then. First question is about definitions. Again, remember I told you often will be asked about some definitions. So first is the definition of just overall enthalpy change of the reaction. So this question gives you maximum 2 marks. So how to answer these kind of questions? So you can tell that this is the enthalpy change when reactants and products react under standard conditions, and this is enthalpy change for given amounts of reactants and products. So for any reaction, amounts could be equimolar or of different ratio. So in that case, enthalpy changes also are different, so you need to specify that. So how would I answer to that question? So I would say that it's enthalpy change when given amounts of reactants produce products, also given amount of products under standard conditions. And you also may add in their standard aggregate states. So sometimes this may give you 3 marks, so you need to understand what does examiner wants to see in your answer. So probably 3rd mark could be awarded for mentioning aggregate states. So for standard enthalpy change, aggregate states are also must be standard. Alright, next question is about Hess law. So you need to state it, and this gives you 2 marks maximum. So according to the curriculums, Hess law, you need to just remember that law, and sometimes you're going to use it a bit later. It says that enthalpy change of any reaction is independent from the path of the reaction. So total enthalpy change, it means that a reaction can undergo in one step, or the same reaction could undergo in several steps by an alternative route. And in both cases, enthalpy change of the reaction when you compare reactants and products will be the same, and that's about Hess law. So Hess law states that total enthalpy change is independent from path or route of reaction. And you can mention that it only depends on initial and final states. That's it. Alright, so this gives you 2 marks. So you need to say that it's independent, so it's 1 mark from reaction pathway, and just say that it depends on initial and final states. Final state, or by state we mean reactants and products of a system. So by a system we consider some reactions or some steps or many reactions. Alright, next question is about enthalpy change and Hess law. So in that question, you need to represent this equation in enthalpy cycle using only enthalpy changes of formation. So first of all, we need to memorize what is it formation enthalpy change. So formation enthalpy change is the enthalpy change when 1 mole of a substance is produced from its elements in their standard states, of course under standard conditions. So you can just start writing this equation first. Just copy paste, then show how would you make each substance in that reaction. So how would you make sodium hydrogen carbonate? So you need to take all of the elements in their standard state. So we need sodium. Sodium is a metal, solid metal in its standard state. Hydrogen exists as hydrogen molecules, H2 as a gas. Carbon exists as a carbon, and we should write it in form of graphite, or you can just write solid, which is also fine. Then we also need oxygen. So oxygen exists as the oxygen molecules in a gaseous form, but it's not done yet. So you need to balance this equation. So we see 2 sodium atoms in this side, so I'm putting coefficient 2 here. We have 2 hydrogen atoms here and 2 hydrogen atoms in one molecule, so hydrogen is already balanced. Regarding to carbon, we need to add again coefficient 2 to balance the equations. Then we have 6 oxygens in this side of the reaction, so we need to triple the amount of oxygen molecules, and this enthalpy change equals to standard enthalpy change of formation of this substance. I'm writing it in the brackets, but so it's solid. It is also important, but this is doubled. So this is enthalpy change of formation of sodium hydrogen carbonate multiplied by 2, because if you remember, standard enthalpy change of formation is when 1 mole is produced, but we have already 2 moles in the equation, so we need to take it multiply it by 2. Also, then you can do the same with sodium carbonate. So I'm just drawing another arrow here. So we need again 2 sodium solid, then we need carbon solid, we need oxygen gas, and let's balance it. So sodium is already balanced, carbon is balanced, oxygen is not. So we have 3 oxygens here and 2 oxygens here. Unfortunately, we cannot change anything here in the main equation, but we can put appropriate coefficient here to balance oxygen. So how to get 3 from 2 oxygens? We just need to multiply it by 1.5, or yeah, just 1.5. If you multiply it by 2, you'll get 3. And then this is an enthalpy change of formation of sodium carbonate solid. Then just write what is left unused. So we're gonna continue this later, and water as well. So you also need to do the same with these substances. So we need to make carbon dioxide from carbon and oxygen, and this is enthalpy change of formation of carbon dioxide. And this is already balanced, so aggregate states must be assigned. Then copy the rest part of the equation. So I'm just going to write water and this part which was before already, so we are not using that part. And then we need to also form water. So to make water, we need to have hydrogen and oxygen. Both are in gaseous states, And we also need to balance it. Hydrogen is already balanced, so we have two hydrogens here and here. Oxygen is not balanced, so it's just 0.5 moles of oxygen gives you 1 mole of oxygen in water. So this is the standard enthalpy change of formation of water. And you also need to copy the rest part of the equation. So carbon in solid, I'm copying this from this side. Oxygen gas, then I'm copying this part here. So it's 2 sodium solid plus carbon solid, then oxygen, 1.5 moles of oxygen gas. Now we need to make a cycle. As you see, we don't have a cycle yet, but we can compare these ends of kind of sets of reactions. So you can compare this part with this part, and if we have all of the species given in same amounts and nothing more, it means we have made a cycle. So let's check it real quick. So we have 2 sodiums here, 2 sodiums here. Hydrogen, we have 2 hydrogens here, we have 2 hydrogens here, we have 2 carbons here, we also have 1 carbon here and another here, so we still have same number of carbons. Then we have 6 oxygens in left hand side, so we have 1.5, 0.5, this gives us 2, and plus 1 gives us 3 oxygen molecules. Whoa, we have the same equation. So what does it mean? We can just erase that part and just continue that like that. So we are making water from these amounts of oxygen and hydrogen here, and the rest elements are left, so we have made a cycle. Sometimes you may see that this process of making sodium carbonate, carbon dioxide, and water is just done in one step. They just simply sum up all of the elements, then sum up all of the formation formation enthalpies. So, which is also fine, but I think this way of explanation is more clear. All right, now the cycle is given. If you want to double check yourself if your cycle is correct, you can also check if all of the atoms are balanced in each side of your cycle. So you must have the same number of atoms in every side of the reaction in your cycle. And if you have it, perfect. You've done it. You don't need to worry about it. Okay, next question is related to that cycle. So you need to use that formation enthalpies to calculate the enthalpy change of your reaction. So the first reaction. And but before, I forgot to tell you how can you earn 3 marks. So 1 mark is usually given for all reactions balanced. So if you have everything in the appropriate amounts, your reaction will be balanced. Then second mark may be awarded for missing or not missing your aggregate states of reactions. And third mark could be awarded for assigning what type of formation or what type of enthalpy changes you're using here in the cycle. So you need to also label all of your arrows here as I did. All right, now how to calculate the enthalpy change of these reactions. So you can label it as enthalpy change of the reaction. So how can you calculate that one? So in order to calculate the enthalpy change of this reaction according to the cycle, from the cycle, you need to go to your from your reactants to your products by your alternative route that you've made, just having some values. So it is, for example, in that case, impossible to measure this enthalpy change of this reaction by just direct reaction. So you can use that alternative route, but be careful. You must go from reactants to the product side. So you need to go in that direction. And if your arrow is against to your direction, you need to take that value with a negative value. If the arrow is against to your direction, you need to take that value with opposite sign. If your arrow aligns with your direction, so you just need to sum up this value. That's it. So I'm just gonna real quick assign these values. And don't forget about coefficients you have in your cycle. So these must be multiplied by this value. So simply the enthalpy change of the reaction equals to, look, this arrow is against to your direction, so I'm gonna take this value with a positive opposite sign, so it's gonna be plus 0.8 multiplied by 2. Then in this case, arrow is aligning to our direction, so we're going to keep this value, and it's still aligning in the further equations. And if you take a look at your equation, so you can figure out that in that case, enthalpy change of the reaction equals to enthalpy change of formation of products minus enthalpy change of formation of reactants, because if you take enthalpy change of reactants, which is the negative value, this is going to turn positive. So you have definitely have seen this equation before, so you simply can take enthalpy changes of formation of products and subtract enthalpy changes of formation of reactants from products, and you'll get the same answers here. But drawing a cycle allows you to not to memorize all of these equations, because for combustion enthalpy change it may be opposite, so you may just have forgotten them or just get confused, and instead of memorizing them all and being not sure on it, you can just simply reproduce it, working out that little tiny cycle. And if you do it very often, you can do it very, very quickly. It won't take so much time as it took when I've explained it to you. So if you put all of these values together, you're gonna have 91.6 kilojoules for this reaction. So usually it's given for 1 mole, but we can just leave it because it's for 2 moles of sodium hydrogen carbonate, and this is for that equation. So we also can double check if we are having the appropriate sign. So as you see, this is a positive value, meaning that this reaction is endothermic, and we can look at our equation and ask ourselves, is it really endothermic, or maybe it's exothermic? Did I confuse myself by putting this formula in the wrong way? So according to our equation, it's a decomposition reaction. So as you see, you have one reactant and many products. So this is decomposition, and mostly decomposition reactions are endothermic ones because they require some heat to produce that products. And yes, you're right, this is an example of an endothermic reaction. All right, so this must be done here, and this gives you 3 marks. 1 mark probably for taking that values in and subtracting them in appropriate way, as I did here. 2nd mark is for units, and 3rd mark probably for your routine calculations. But if you just have shown the final answer, you sometimes maybe just be given all of the marks with no further checking. It means that you have done it in your calculator and you don't want to put them here, you don't want to waste your time by writing it, but I suggest you to show calculations here, because sometimes your examiner will be seeking for your operations. So every step is important here. And also please don't forget about units, because this usually gives you one more mark. Okay, next question is about, again, enthalpy change of formation, and this is the definition of it. So enthalpy change of formation. So as you see, it gives you 3 marks and you need to guess, how can I get all of these marks? So you need to memorize all of these equations and all of these definitions, and assume which bullet points are important and gives you marks. So first, according to the definition, it's an enthalpy change when 1 mole of a substance is produced, so it's important part. Second mark is given for saying that this is the enthalpy change when 1 mole of substance produced from its constituent elements. And third mark is given for mentioning that these substances, all of them, reactants and products, are in their standard aggregate states, and this reaction is carried out under standard conditions. So that is how full answer should be given. So first, 1 mole is of substance produced. Second, from its elements. From its constituent elements. And third mark, under in their standard states and conditions, standard conditions. All right, let's move on to the next part. So this is the task to calculate formation enthalpy of the reaction from combustion enthalpies, and this also requires some skills of drawing cycles. So I'll show you that again, but we are going to do that using different values in our cycle. So first of all, we need to represent the equation that we are going to use as a basis. So this is formation enthalpy of ethylene. So we're going to write it as a product. So it must be in its standard state. So hydrocarbons with 2 carbons are often gases under standard conditions. And formation enthalpy, it's an enthalpy change when 1 mole is produced from its considered elements in their standard states. So it must be solid and hydrogen gas. And don't forget to balance it. So we have 2 carbons here and 2 hydrogens here. That gives us the appropriate amount of atoms in the right hand side. So we need to find out the enthalpy change of formation for ethylene. Then we have to use only combustion enthalpies for ethylene, carbon, and hydrogen. So we need to memorize what does it mean, combustion enthalpy change. So according to our definition, combustion enthalpy change is an enthalpy change when 1 mole of a substance is burned completely under standard conditions, or is burnt in excess amount of oxygen, which is the same for complete combustion. So you can just work out these equations for yourself. So this equation can be used to represent combustion enthalpy change for carbon. So it's solid, gas, and gas. And the next one is for hydrogen. So for hydrogen, be careful, because it must be for 1 mole of hydrogen. So we need to put coefficient 0.5 here. You cannot simply double this and this to get oxygens with the whole numbers. No. So this is combustion enthalpy of hydrogen. So gas, gas, liquid. And for ethylene, it's gonna be C2H4 plus oxygen gives us CO2 and water. And also this must be balanced in such way. So 4, 8, so we need to put 4 here. All right, so we need to use all of these three equations to construct a cycle. So what can we do? Again, we can burn carbon, but we don't have any oxygens in our equation. What can we do? Well, this is an interesting part that has lots of parallels with mathematics. So in mathematics, you can sometimes introduce some values. But if you're introducing them in one part of the equation, you need to introduce them in the another part. So you cannot simply add anything you want. You have to do that in that amounts that will cancel out each other. So we need to burn 2 moles of carbon, but we have in combustion enthalpy change of carbon, we have 1 mole of oxygen. So it means we need to have 2 moles of oxygen gas, and these two together give us 2 moles of carbon dioxide gas. And this is combustion enthalpy change for carbon multiplied by 2, because you see we have 2 moles of carbon burned. And we need to write the rest of the reaction here. And don't forget to add the same substance that you have added here in same amount. So we have 2 oxygens here. All right, now we also can burn hydrogen. Again, we don't have any oxygens here, but it means we can add more. So we need to burn 2 moles of hydrogen. As you see from our equation, we have 1 mole of hydrogen. So we need to double this amount of oxygen again. So it's going to be 1 mole of oxygen. That gives us 2 moles of water. Then this is equals to combustion enthalpy change of hydrogen, again multiplied by 2. So hydrogen is a gas. And I'm going to also write the rest of the reaction. Also, don't forget to add that oxygen in the rest of the equations. So I've added 1 mole here, so I'm adding it here again. And I also need to add it here because if you're not doing this, oxygen will not be balanced. So you won't have same number of oxygen atoms in all of these reactions. And if you remember, that was one of the requirements for the correct cycle. The last one, so we have to burn the product. So according to that equation, to burn 1 mole of ethylene, so we have 1 mole here, we need 4 moles of oxygen. Hold on. So 4 plus 2, so it must be 3. It wasn't balanced properly here. So we need to have 3 moles of oxygen. So we need to check if we have this amount of oxygen. So we see that oxygen is already here because we have balanced it before. So, and we have that exact amount of oxygen needed to burn. So you see 2 plus 1 gives us 3 moles of oxygen. And this gives us 2 moles of carbon dioxide gas plus 2 moles of water liquid. So, and this is standard enthalpy change of combustion of ethylene. And again, look at the ends of your kind of a cycle. It's not a cycle yet, so we have 2 carbon dioxide and 2 water molecules here. And as you see, we also have the same amounts here. And it again means that we can simply connect them. So I'm gonna erase this and just connect this like that. So that's it. Now we have our cycle and it's balanced. Then it's not an end, so we need to calculate the enthalpy change of this reaction. Again, if you remember, we need to use the cycle and we need to go from reactants to the product side, but we need to go using that alternative path. And in order to find this enthalpy change of the reaction, so this is formation enthalpy in our case, formation enthalpy for ethylene. gas. It equals to, as you see, this arrow aligns with our direction, so we can keep this value. So combustion of carbon in graphite, as you see, it's minus 394 multiplied by 2. Don't forget about these coefficients. Then in this case it also aligns with our direction, so this arrow aligning. Combustion enthalpy of hydrogen is minus 286 multiplied by 2 again. And lastly, here you see this arrow is not aligning with our direction, so we need to take combustion enthalpy change of the ethylene with opposite sign. So it must be plus 1411 kilojoules with no any coefficients. As you see, we have 1 mole here only. And if you have a look at this equation, so you'll see that in that case, formation enthalpy change for this case equals to the enthalpy changes of combustion of so this is gonna be reactants minus enthalpy changes of combustion of products. So we can compare it with the previous outcome that we did, so reactants minus products. And as you see here, products minus reactants, but if you're using formation enthalpies, for combustion enthalpies it's absolutely opposite. So if you don't want to just memorize this overall equation, you can just work out this cycle and use it. You'll get the same result. So let's do that routine calculations. Kilojoules. And be careful, this is given in kilojoule per mole, per 1 mole of your substance. So this makes sense. So this is 51 kilojoule per mole. Okay, let's move on to the next part. Now we need to calculate combustion change, enthalpy change of combustion for the same substance, but using bond energies. So again, we need to first begin with the equation taking place here. So this substance is burned in sufficient amount of oxygen to give us only these products. Okay, so this is enthalpy change of combustion, and we need to balance it first. We have to double this, and triple this. Then if you're using enthalpy changes, so bond energies, so you need to know what type of bonds are here, and it's better to work out the displayed formula of your products and reactants. So ethylene, it's an alkene, so you must show the double bond. So we have double oxygen double bonds, and we have 3 of them, and we have structure of carbon dioxide, which is looking like that, and we also have 2 of them, and we have 2 water molecules with bonds, single HOH bonds. Now we need to understand what is happening during the reaction with bonds. So in any reaction, bonds are broken in reactants and bonds are formed in the products. So you can simply assume these changes, taking these values with appropriate signs. So bonds are broken here and formed here. And bond breaking is an endothermic process, so it needs some energy. So enthalpy change for bond breaking process is a positive, and it's opposite for formation. So you can look what type of bonds you have and how many of them you have. So we have 1 carbon-carbon bond, so we need to break 1 carbon-carbon bond. We also have carbon-hydrogen bond, and we have 1, 2, 3, 4 of them. And we have oxygen, double oxygen bonds, and we have 3 of them. Then, so all of these values should be taken with a positive sign. So these, and formation process, so we have carbon double bond oxygen bonds, and we have 2 bonds in one molecule, but we have 2 molecules of them, so it's 4 bonds carbon double oxygen bonds. And we also have hydrogen and oxygen bonds. We have 1, 2, and multiplied by 2, it's again 4 bonds. And these bonds are formed, and this process is an exothermic process, and this is a process, well, this is an enthalpy change with a negative sign, so we need to take them as a negative value. So simply, enthalpy change of any reaction could be calculated by enthalpy changes by sum of enthalpy changes of bonds broken minus sum of enthalpy changes of bonds made or formed. So by putting all of these values here, so we have carbon double bond carbon here, so probably here is the mistake, so it must be double bond, so it's 839 plus 4 multiplied by CH bond, so CH bond equals to 412 kilojoules, plus 3 multiplied by oxygen double oxygen, which is 496, and minus finally 4 multiplied by carbon double oxygen bond, so this is 805, and minus 4 multiplied by hydrogen and oxygen single bond, which is 463. And you'll get some value, and this value for sure must be negative value. It's gonna be equal to some value, and values are units are kilojoule per mole. So you'll get first mark for taking these idea. So if you're using bonds broken minus bonds made, if you're using that idea, if you're following it. Second mark for the proper calculations and your value here. Third mark for the appropriate sign, and the last mark for your units. So as you see, all of these parts are important in your answer, so please follow it. Alright, if you do the routine calculations, so you must have this value, negative 1097 kilojoules per mole. Okay, now let's move on to the next question. So this question is related to the calorimetry technique. So first, the experiment has been set up. So during the experiment, propane was burned, and it raised the temperature of certain amount of water by some values, and we need to first find out how many moles of propane was burned. So very easy stuff. So in order to find moles of propane, we simply need to use that formula, and just by applying for any gaseous substance you can apply these formulas. So in order to find moles, you need to simply divide molar its volume by a molar volume, and at room temperature and pressure, molar volume equals to 24. So 240 centimeters cubed divided by 240 decimeter cube per mole. So as you see, we have different units, so it means we cannot simply divide them, so it's just 24. So these must be turned into decimeters cubed, just dividing by 1000, so it's gonna be 0.24 divided by 24. Don't forget about units. In this case, units are not required because it's already in the question, but still, it's your literacy. Next question: what is the heat change of these experiments? So we need some values above. So heat exchange of this experiment, so you can calculate heat of any reaction in calorimetry using that very famous formula, where C is specific heat capacity of a substance that you're heating. So we're heating water, so it's given 4.18 joule per gram in Kelvin. Then we need to take a mass of substance that being heated. So this is again water, and we have 150 centimeters cube of water. So we cannot use volume of water, we need to transfer it into mass. So as you remember, mass equals density by volume, and we know that water has a density equal to 1000 grams per centimeter cube. So simply this equals to grams, so it's 150 grams, so we can just keep it here using the same value. Then we need to multiply it by the heat difference, so or heat raise or drop. So it's already calculated here, so you don't have any final and initial values, it's already given. So it's in Celsius, but no matter you take Celsius or Kelvins, they're going to cancel each out, and this is just a difference. It won't impact on your results. So no matter you're taking this difference in Kelvins or in Celsius, it will be the same. Then just put everything in calculator. And what are the units for your value? It's joules. So this amount of heat was absorbed. So heat change of this experiment is this. Then we need to find out what's the molar enthalpy change of combustion. So enthalpy change of any reaction carried out, and if you have all of these data like above, can be calculated from this formula. So you simply are taking heat exchange and dividing by moles with a negative sign. So also you should remember that enthalpy change is given in kilojoules per mole, so you need to transfer heat into kilojoules. So I'm simply dividing these into I'm dividing these by 1000, and this gives us 20.006 kilojoules, and I'm using it here. And divided by the number of moles substance reacted. So please don't be confused by putting moles of water here. Nope, it's moles of propane gas that we have here, which is 0.01 moles. 0.4 kilojoules per mole. So that's how we calculate the enthalpy change of any reaction from the experiments related to calorimetry technique. Then we need to also calculate the enthalpy change for complete combustion of propane using formation enthalpies. So we can apply the method we utilized before. So in order to calculate, so first we need to construct the equation. So propane gas is burnt completely to give carbon dioxide and water. So water is liquid, this is a gas, gas, and gas. Also, please don't forget to balance your equation. So we have to balance it this way, and we have 10 oxygens, so we have to put 5 here. Yep, so 6 plus 4 gives us 10, and 5 by 2 gives us 10 again. So Then we can go back to our calculations. So we need to find out the reaction equation from formation enthalpies. So I actually don't remember what was that formula, so this is why I'm always using Hess cycles. So let's go back and check what was the formula actually for formation enthalpies. So we see combustion. So for formation we need to take enthalpy formation enthalpies of products minus reactants. Then I'm going to apply this formula, and I can double check myself just looking at the value we have. It should be a negative because this is again a combustion and combustion reaction, which is an example of the exothermic reaction. Okay, so formation enthalpy of products. So carbon dioxide, 3 multiplied by formation of carbon dioxide, which is minus 393.5. Plus formation enthalpy of water, 4 multiplied by formation of water, which is minus 285.8. Then we need to subtract enthalpy change of formation of the reactants. So for propane it's minus 104.7. Then we have oxygen, and we don't have any enthalpies of formation of oxygen because formation enthalpies of simple compounds always equals to 0 because they already are formed. You don't need to apply any effort to make them, so they are already there. So that's it. Okay, let's and as you see, we are having a negative value, so it's just simple routine calculation. So yeah, the formula was right. You can memorize it for yourself if you want to, if you don't want to construct the cycle again, but still possible to do that by two ways. All right, now we need to compare these results from calculated ones. So this is calculated value, and experimental result is minus, oh, I forgot to put negative sign here. You see, it was here, but I forgot to do this here. Don't do that. You'll be punished instantly by reducing your mark by 1. So that's what not to do. It's very easy to get frustrated and do that mistake. So this is kilojoules per mole. So experimental value is this. The calculated one is more exothermic. So we need to explain why we have such a difference, and this gives us 2 marks. Okay, what can you propose here? So look, calculated value is more exothermic, meaning that some energy was lost during the experiment, so you can actually focus on this. So you can say that there was heat loss during the experiment. Secondly, you can say that reaction was, even if you carry out this experiment in a perfect calorimeter with 0 heat loss coefficient, so you're probably also not having the exact value, maybe very close to it, but again there will be some inaccuracies, and this is explained by the reaction that is not taking place completely. So you can say that, you can actually write down here that combustion reaction was not complete. So reaction may undergo not completely. And these 2 points are very important, and probably they are paying a lot of effort, and they play a key role in that difference. Alright, let's move on to the next question. So, some organic substance containing hydrogen, carbon, and sulfur is burned. And you need to show the reaction equation for that process. Very easy. So, look at the conditions. So, it's complete combustion. So, you have to make oxides of elements. So, don't forget about state symbols. There are 2 marks for that, and probably if you forget them, you'll be punished by lowering your mark by 1. So it's a liquid, it's already given, don't forget about it. We need to put oxygen gas. And products, what are the products in that reaction? So the product are oxides, as I mentioned before, but for complete reaction is carbon dioxide gas, water, liquid, and sulfur dioxide. We don't have sulfur trioxide in these reactions because sulfur and sulfur containing substances produce sulfur dioxide when burned. Only this. Sulfur trioxide is made in presence of catalyst, so be careful here. Now we need to balance the equation, so this is your second mark. First mark probably for the correct products and state symbols included. Second mark probably is for proper balancing. So we need to simply balance the equation. So we put 4 here to balance carbons, we put 2 here to balance hydrogens, so sulfur is already balanced. Now let's check oxygens. 8 plus 2, 10, 12, so we need to put 6 here, and now the reaction is balanced. Next. Alright, student carried out this experiment, and again, some definitions. There are 2 marks for that definition. So enthalpy change of combustion according to lots of resources, it's an enthalpy change when 1 mole of substance. So this is a bullet point. A second bullet point is for mentioning that it was burnt in excess of oxygen, or it was burnt completely. So 2 bullet points. Next question. Yeah, you again need to apply these math. So heat released during experiment is again calculated by that formula. So heat capacity of water is this. Mass of a substance heated, water, it's already given in grams. Perfect. Then we need to multiply it by a temperature difference, which is 19. So simply put all of it in your calculator. Joules. Yep. Yeah, it's already given in joules. So first mark probably for utilizing that formula, second for proper calculations with units. Next, you again need to calculate the enthalpy change of combustion for this experiment using the previous formula. So don't forget to transfer it into kilojoules. So I'm already putting this value negative divided by 1000, and we simply divide these by moles of thiophene. So it means we need to find moles of thiophene. So now we need to use that formula, mass divided by molar mass of thiophene. So mass is given 0.63. Molar mass, I assume it's all again somewhere around 63, or value that can be divided by that number. So moles. And let's put it here. Yeah, don't forget about units, and that's all of the calculations that you need to show in your answer. Next question. All right, so again, some definitions. Bond energy definition, again 2 marks. So there are lots of variations of these definitions, but mostly they consider almost the same things. So it's an enthalpy change when 1 mole of covalent bonds broken in a gaseous state. Sometimes you can specify to produce gaseous atoms. Makes sense, but this is just 2 marks, so you can just leave it as it is. So when 1 mole of covalent bonds are broken, it's 1 point, and for mentioning that it's a gaseous state, it's a second point, because if you take its standard state of any substance, you cannot consider these values as standard bond energy values. Nope. They always are given for substance first being in a gaseous state, then giving atoms of its compound. Then atomization enthalpy for any element is, again, according to definition, very common ones. It's an enthalpy change when 1 mole of gaseous atoms are produced. It's a bit different from bond energy, but usually it's just half of bond energy values. So it's when 1 mole of gaseous atoms are produced. So it can be produced by breaking some covalent bonds, or if you take, for example, sodium. Sodium usually exists as a solid substance, and you simply vaporize it, and vaporization enthalpy is equal to atomization one. So it's not always about the bonds, covalent bonds, and atomization enthalpies. They are not often related to each other. I mean, they are related to each other, but not always. Okay, next question is about using bond energies and atomization energy and construction of a cycle. It's a bit rare question, but still you can find some questions like that. So we need to find out the bond energy of this bond. So what is bond energy value? So we have this in a gaseous state, and that gives us hydrogen gas, gaseous atoms, and bromine gaseous atoms. So that is the enthalpy change that we need to find out. Then what do we have? We only can use these values. So we have formation enthalpy for hydrogen bromide. So formation enthalpy, according to the definition, it's an enthalpy change when 1 mole of a substance produced from its constituent elements in their standard aggregate states. So hydrogen and bromine, they exist as diatomic molecules, but we need to take half of both because we are making 1 mole of it, and this enthalpy change is given, and it's equal to minus 36.2 kilojoules. So this amount of energy is released when these two substances react to give hydrogen bromide. What do we also have? We have atomization energy of bromine, so it's when 1 mole of gaseous atoms are produced. So we can show it like that. So this is delta H atomization of bromine, and this is also given, so it's positive, this value. Again, I'm just leaving some space for this species not involved in that transition, and we again have atomization enthalpy for hydrogen. It's again when 1 mole of these gaseous atoms are produced from doesn't matter what, so from its element. So it's standard enthalpy change of atomization of hydrogen, so it's gas, it makes sense, and this equals to, again, positive 218 kilojoules. Now we need to find out the enthalpy change of this reaction, which is the bond energy. All right, again we are following that rule in cycles. So we need to go from this to the product side, so using the alternative route, which is this. Okay, so enthalpy change of this reaction, or bond energy of hydrogen bromide gas, equals, so our direction is against to that arrow, so we need to take this value with the opposite value, with the opposite sign, so it's positive 36.2. Then in these cases, these arrows are aligning with our direction, so we can just keep them. There is no need to put any coefficients in that case because everything is given for 1 mole and we are completely fine with that cycle, and cycle is actually balanced. So let's put everything in calculator. 366.1 kilojoule per mole. So this gives you 2 marks for construction, for making a cycle, and 3 marks for calculations with the answer. We can ensure if we have a correct value just looking at the equation. As you remember, bond enthalpies are enthalpy changes when 1 mole of bonds are broken, and if you remember, bond breaking process is an endothermic process and the enthalpy change is a positive. You see that, and it means that you did it right. There is nothing to worry about and you can go further. Alright, thanks for watching. Please like, share and comment if you want more videos like that. See you soon. Bye bye.